top of the screen I've got the formula for the nth order Taylor polynomial for some function f with the center at a. And that formula is always going to start with the function evaluated at a, then the first derivative times x minus a to the first power, plus the second derivative over 2 factorial x minus a squared. The next term, I ran out of room, would be the third derivative f triple prime of a over 3 factorial times the quantity x minus a cubed, and so on and so on and so on to the nth derivative evaluated at a divided by n factorial times x minus a to the nth power. Now if I want to find Taylor polynomials centered at the origin, so that's going to be centered at the point 0. We're talking about a value of x for n equals 0, n equals 1, and n equals 2. Alright, so n equals 0 is going to be the Taylor polynomial that just has the x minus a to the 0 power on it. N equal 1 would be the Taylor polynomial with these first two terms, where we have a factor x minus a to the first power, and then n equal 3 would be the Taylor polynomial that encompasses the first three terms. So we're going to need the function, we're going to need the first derivative, and we're going to need the second derivative. And we're going to need those evaluated at x equals 0. So f of 0 would be 1. F prime of 0 would be -1. And the second derivative evaluated at 0 would be 1 again. So our polynomial function p sub 0 of x is simply going to be f of 0. So that function is p of x equals 1. P1 of x will be f of 0 plus f prime of 0 times x minus 0 so that would be P1 of x, oh, and we've got slow computer today, is 1 minus f prime of 0 times x minus 0 to the first power. Oh my goodness, there we go, 0 to the first power. So P1 of x simplified is 1 minus x. Then P2 of x, f of 0 plus f prime of 0 times x minus 0 to the first power plus f double prime of 0 over 2 factorial times x minus 0 squared. So cleaned up, that would be 1 minus, well, those first two terms are simply 1 minus x. Okay, it's P1 of x. Plus, then we're going to have the second derivative evaluated at 0 divided by 2 factorial, which is 2, times x minus 0 squared, or just x squared. squared, not 0. There we go. So our second P2 of x, second degree Taylor polynomial that can be used to approximate e to the minus x power, centered at x equals 0, is 1 minus x plus 1/2 x squared. 1 minus x plus 1/2 x squared. Okay, now I've got the original function f of x and then p0 of x, p1 of x, and p2 of x, all in my calculator. And I want to look at a graph, and what we want to focus in on is how close do these equations come to approximating the function f of x. So let me start out with just looking at f of x and p0 of x. Okay, our constant function p0 of x is equal to 1. The only thing that function has in common with the original function f of x is the value at x equals 0. And you look at that graph and you think, well, that curve doesn't approximate f of x at all. And you're really right. But it does share the function value. If I get in here and I turn on the linear function, we can see that that linear function actually comes a lot closer to approximating the curve for e to the minus x power. And what's going on there is that linear function shares the value at x equals 0, and it also shares the slope at x equals 0. If we look at our quadratic function, okay, we see that that curve, because there's some curve, fits the curve better. And all three of these equations share the point 0, 1. But what's happening with our quadratic function, which was the last thing that you saw graphed there, is that we have the same function value, we have the same slope at x equals 0, and we have the same concavity at x equals 0. So the function value, the first derivative value, and the second derivative value are all equal. And the idea is the more terms you have in your Taylor polynomial, the more closely your polynomial will approximate the actual function. Now, these are approximations, so they're not perfect. There is some error, and we need to remember that the absolute error is going to equal the absolute value of the difference of the function f of x minus the polynomial Pn of x. Now, before we talk about error, I should do some approximation. So let me move that out of the way. Okay, if I wanted to use my polynomial functions to approximate e of negative 0.1. Okay, thinking about our original function is f of x equals e to the minus x power. What I'm looking at here then with e to the minus 1 power is a value of x that's equal to 1/10. So to approximate using, I'm not even going to go with P0. I'm going to start with P1 of 0.1. Okay, our equation was 1 minus x there, so we'll have 1 minus 0.1. So the approximation would be 9/10. Using the second degree Taylor polynomial, P2 of 0.1, we'll have 1 minus 1/10 plus 1/2 times 0.1 squared. And of course you can use your calculator to evaluate these, and if you had more than 2 or 3 terms, you definitely would want to let the calculator do that work for you. That value is 0.905. That's a 5. Okay, so if we wanted to calculate how much error we had there, then the absolute error would be e to the negative 0.1, we'll have to use our calculator for this, minus the polynomial approximation, so 0.9 if we're using the first degree polynomial. And that error in this particular case is 0.09516, and so on. The amount of error, if we're using the second degree Taylor polynomial, is e to the minus 0.1 minus 0.905. And I'm taking absolute value because we really don't care if we're overestimating or underestimating. We just want to talk about how close we are. You know what? That number is wrong. Uh-oh. I need my eraser. There we go. That number should be 0.00483, and so on. Our second amount of error is even closer. 1625. Now what I want you to observe there is that we have a smaller amount of error when we use the polynomial approximation with the higher degree. The second degree function gives us a closer approximation than the first degree function. A third degree function, if we went that far, would give us a closer approximation. So the closer your particular value of x, in this case 0.1, the closer that is to the center, to the value that the polynomial is centered around. In our case, our function is centered at x equals 0. Because 0.1 is very, very close to 0, then we get relatively decent approximations. So you can guarantee yourself a smaller amount of error 2 ways. You can look at values of x that are closer and closer and closer to the point where the function is centered, where the polynomial is centered, or you can use polynomials with higher and higher degrees.